Hello everyone. So starting from this lecture, we are going to work on sequential logic, and it's different from the combinational logic we learned before. So, for example, digital logic, it's usually there are two main parts. The first one is combinational logic. The second one is sequential logic. So the combinational logic we learned starting from the first lecture of this class, including all these, for example, adders, mux, non-gate, and all the other gates, logic gates. So these things are all considered as combinational logic. So the reason is they are kind of static. You give an input. If you know the logic, you can predict the output. And this will be the pretty unique output you can get. And there's no any surprise. It's kind of just static logic over there. But for the sequential logic, it is different. So in sequential logic, the present output depends on the present input as well as the past output. So you have a sequential logic, and you have an input, and you have an output for the sequential logic. Here is the output, right? So if you have an input, you don't even know what the output will be. Okay, there's something else is trying to determine the output as well. So which is the past output. Okay, and you need a little memory. You don't want to directly short your output to the input. So you need a little bit of memory to do this, to send the previous output to the input sequentially, okay? But not just like at the moment you are giving an input, you are giving something magically from the output. It won't happen because there's a sequence. You have all the gates logic in the block, in the sequential logic block. So they will create a lot of delay, and that delay will delay the output from the input. So you give an input, delay, some time delay, you get an output. Okay, and the output will be sent to the input for the next cycle to run the logic, and you get another output. There's a delay here. It doesn't like everything is being cycled without any limitation. It is not. You have delay, which gave a chance for the output to be stored somewhere for a little bit and then being sent to the input. And this kind of thing, you have been heard this a lot. So this is one thing of feedback. Sorry. So the output is being feedback to the input and participate in the logic operation here. So that's a sequential logic. And there are several things we want to learn for this in this course. Some important sequential logic circuits we need to learn. For example, the first one is Latches. Latches, flip-flops, and counters, shift registers. Yeah, I think that's it. We are covering this pretty basic fundamental sequential logic blocks, starting from the latches. Okay, so the latches, then we use latches to build flip-flops, and we use flip-flops to build counters and shift registers. And then we'll do the simulation. You know how to design the counter and shift register by yourself. And that's what we are going to learn in this class. Okay, so now let's take a look at latches first. The first one is called SR latch. The reason it's being called SR latch because this latch is trying to set and reset a circuit. So set means if you give a 1 to it, it's going to set the result to be 1. All right, so that's a concept for set. For reset, it's different. So it's if you give a 1 to reset, you are going to reset the entire circuit, the output, to be 0. Keep in mind, you're always giving a 1 to turn it on. You give a 1 to the set function, you turn it on, you deliver 1 to the output. You give a 1 to reset, you turn on the reset function, you deliver 0 to the output. That's a fundamental, the basic concept for set and reset. Before we get confused a lot here. Yeah, and then there's a NOR gate, SR latch. Let's take a look at this circuit first. You need a one NOR gate, another NOR gate, and this one feedback to there, this one feedback to there, and you have 2 inputs here. So you call this one Q, this one Q bar. Okay, and now here's the first question. If this is given, do you know which one is set, which one's reset? So for example, Q is the output we're going to use. This one, just inverse the version of Q, but that's the output we are interested in. So which one is set, which one's reset? And there's one rule here. You only turn on set or reset individually at one time. So which means you're not giving 1 and 1 to set and reset at the same time. If you just want to set the circuit, you just give a 1 to set, and you must turn off reset. If you want to reset the circuit, you give a 1 to reset, and you have to turn off the set function. Okay, so which means set is 1, reset is 0, so Q should equals to 1. So which means you are trying to set the circuit, and if you have set to be 0, which means you turn off the set function, but you turn on the reset function, Q should be 0. Now let's see if we have this conclusion here, and this is given, and let me know which pin here, which input is set, should be the set function, and another pin should be reset. Now let's try it. If we label here as set, here as reset, and see if that is correct. Okay, so now let's see. If we give this guy 1, this guy must be 0 because we only turn on one function at one time. And because it's a NOR gate, so 0 won't give you a determine or decide the result because you have another input. You don't know what is that. However, 1 being given to the NOR gate, you know 1 is a killer for the OR gate and also for the NOR gate as well. It's going to give a result for 1 for the OR and 0 for the NOR, right? So if you have a 1 in either of the input, you can have a 0 for the output, definitely. So we got a 0 here. And 0 being feedback to here, and R is 0, this is 0, 0, or 0 is 1, NOR is going to be 1. So that's valid because you have QQ bar, which is valid for the design, since we need this one to be Q, this one to be Q bar. That's just by the concept. It doesn't matter, okay? But let's look at that's not that important. Which is important is, let's see if our output is being set. Since we are setting the circuit, but our output right now is 0. It's not being set, right? If you want to set the circuit, you need the result to be 1, and it's not right now. So what you want to do is, this is not right. So it must, since there are only 2 options, it must be this pin must be R, this must be S, right? Now let's verify that if that is true. So if you want to reset the circuit, we need this one to be 1 and we need this one to be 0, right? And then we know that 0 is not going to affect the OR gate, but 1 will. So you are going to get a 0 here, and 0 being fed back, you get a 1 here. And you are trying to reset the signal, you need the output to be 0, and right now it is. So now it's just being verified, which means this pin here should be R, this pin here should be S. So that's called SR latch. Okay, that's a circuit for the SR latch using a NOR gate. So now why is a latch? Okay, so we just analyzed S is 1, R is 0, or S is 0, S is 1, R is 1. However, what if both R and, let's do it here. What if S is 0, R is 0, what's going to happen? Now let's see. If this is 0, this is 0, so zeros won't affect the result for the OR gate or NOR gate. So whatever has been feedback here will be the result, but inverted. Okay, so Q will be Q bar come over here will be Q. And nothing being changed, right? So after a little delay through the gate, Q bar is still Q bar here is you get inverted, you still got a Q here. So which means it's working as a memory. So it's like a latch, right? It locks the previous result of Q and Q bar at the output. If you give a 0 and 0 here, and we'll see an important implication for this one pretty soon. And this is really useful. And you can see that why we can use a memory, why we can have a memory in the circuit, because we have a latch. We can store it. We can store it here. If you give a 0 0, whatever the state was, it's going to be stored as these 2 points here. Okay, that's why that's a memory circuit. And now what about the last case here? If we have S is 1, R is 1, what's going to happen? Let's see. If you have 1 1, so 1 will kill the OR gate, right? And now you got a 0 0 here. It's not making sense. Why do you do that? You need a flip-flop, you need two outputs here to be inversed, and a memory sometimes, you want to set and reset. But this, it's going to work electrically, but it's not making any sense. There's no applications for that. So this is not used. Keep in mind, this is not being used for the NOR gate SR latch. So there's a different circuit for the SR latch, so you can use. So that's the first one. That's latches, right? We introduced latches. That's A, NOR gate, and now we have B here, which is non-gate SR latch. Right? So after I have this circuit here, I'm going to ask you the same question as I just asked you before. Assume here's Q bar. Okay. Which one is R, which one is S? So Q, still, that's the output. Okay. Which one is R, which one is S? And now let's assume this is S, this is R. If we want to set the circuit, this one must be 0. We must turn off the reset function, and 1 won't affect the AND gate and NAND gate. But for 0, it's going to kill the AND gate, give you a 0, and then being inverted, you got 1 here, and 1 will be fed back to here, and you have 1, 1. Right now, you can get a result, confirm the result, which is going to be 0. So you're trying to set the circuit, but finally the output becomes 0. It's not the one you expect. So this is not the correct label. So actually, there's another, just 2 options, right? If this is not right, then it's going to be RS. And you can verify. You don't have to memorize all these things. You can verify this later for the next time if you get confused. But now you know this is R, this is S. We can verify this really quick. So if we want to reset the circuit, we give a 1 to reset function, and we give a 0 to set function, so to turn it off. But reset function right now is on, and we let's see, R won't affect the NAND gate or AND gate, but S will, because you got 0 here. So 0 will kill it, give you a 1 here, and 1 being fed back, you get a 1, 1, 1, you get a 0. So you are trying to reset the circuit by turning it on, and now you get a 0. So the output is being reset, which is correct. So that's a valid version. And if you there's easier way to memorize this in the future if you don't need to derive this all the time to save your time. So not only the NAND gate SR latch, but also for the NOR gate SR latch, if you have the Q, which is the output, designated output on the top, then it's going to be RS like that. RS, RS. So R will be on the top. This is pretty easy to remember. So you don't need to derive this all the time, which is wasting your money, wasting your time. Now let's take a look at this. The conclusion here is if we reset the circuit, we are going to get Q will be, since we are resetting that, let's reset. If R is 0 and S is 1, sorry, it's not a good writing. And then we are setting the circuit so the result will be 1 and the inverse the result will be 0, and we are setting the circuit. So what if R is 0 and S is 0? Remember previously we have the NOR gate SR latch. If you have both of S and R to be zeros, it's a memory. But now it can be a little bit different. If you have a 0 and 0 here, you're killing the two AND gate or NAND gate. You're getting a 1 and 1 to here to the outputs. We need this one to be, these two to be inversed, because it just depends on applications in the future. Electrically, it works, but however, this is not being used because we are not getting an inverse outputs, two outputs here, and it's not just not useful. What about R is 1, S is 1? So 1 won't affect the NAND gate, right? So it's totally depends on the other side of the inputs. And now Q bar will be fed back to here, will still be Q bar and being inverted, and you got a Q. Q being fed back and inverted, you got Q bar. So nothing will be changed. Q will still be Q, Q bar will still be Q bar. Depends on what their initial status are, they will stay there forever. So it's going to be a memory. So there's a difference if you compare the two different SR latches. One is a NOR gate SR latch, another one is the NAND gate SR latch. The difference is, but here's no difference for the order for the R and S. It's also both of them have R on the top, S at the bottom. But the difference is here for the NOR gate. If you need a memory, you need both R and S to be zeros. But for the NAND gate SR latch, if you need a memory, you need both of them to be ones. That's a major difference you need to know. And the NAND gate SR latch is being more often used in applications. So next, I'm going to introduce one application here. Application 1, right? So this is a debounce, switch debouncing. The reason we need that is in a circuit looks like this. That's a NOR gate SR latch, and we need another one here, and this one here, and feedback, right? Y1, Y2. That's two outputs. I mean, you can use this one as a switch to turn on something, for example, an LED, or anything else, right? But this is just a switch. It's just to providing power to the external load, external circuit. So that's a SR latch. Everybody knows that right now, and that's a pull down resistor. Both of them. It doesn't matter what's the value. It's the application for these two resistors are just trying to give so whenever if you don't have anything to be connected to that, you still have a circuit, you have a loop. You have this pin to be grounded, so which means you are trying to apply a pretty strong 0 volts voltage source here, which is a ground, since there's no current flow through the circuit, so no current flow through, I equals to 0. No current, no voltage drop, so 0 volts here, 0 volts here, right? So that's how you can give a pretty solid 0 to the circuit when you have nothing to be connected to the input here. And this will be pretty useful, remember that. So this is a 0 volts, it's trying to pull this pin to ground, right? That's the purpose of these two resistors. If you don't connect anything here, that won't be 0 volts. It's going to be a floating pin for whatever voltage is. I just don't know, but you need a solid ground to ground it solidly to make it to be a 0 volts over there. So that's a logic 1 at this pin here, for example 5 volts, okay? And in the beginning it is here, it is at that pin, or let's starting from here. So here's A, here's B, okay? So the switch is being closed at this point. We can start to draw a timing diagram for this circuit. Let's use the same page so you're not getting confused. So if set B is on, A is off, what is Q? Which one is Q? So the first question is, if B is on, A is off, which means logic 0, which is Q, which one is Q, which one is Q bar? So if B is on, A is off. If here is on, 5 volts, and here is 0 volts, you give it to 5 volts and 0 volts here. So which one is being set and which one is being reset? You give a logic 1 here, logic 0 here, since we know it's RS, right? So it's RS, so which means if you give a logic 1 here, you are going to reset the circuit. So here will be the result will be 0. You are going to turn off the Q. It shouldn't be which is Q, which is what's the output? Not this. What is the output? What is the output? Okay, that's the first question you want to think about this before we move forward. And now the second question. Why this one can be used as a switch debouncing application? So we need to know what is debouncing. Why the circuit can be used for switch debouncing. So what is debouncing? So why do we need that? So whenever actually, you won't be able to notice that, but when you have a switch, electrical switch, for example, like this, you're trying to move it, and then there's a metal piece inside, you're trying to turn it on, turn it off. So when you are doing that, because they are all mechanical materials, you won't have a solid on and off. What instead is going to happen over there is the mechanical material is going to vibrate and to turn on and off that point for a few times, which is really minor effect and phenomena you won't be able to notice, but actually it's happening. For something like this, you want zero vibration, because any vibration will change the result and lock it to that status permanently. And let me draw a timing diagram to show you the details for that. Why is that? So for example, there's I put it to A here, and there's a the following circuit I didn't show you over here, and now you have a B here. So that's a 5 volts logic high. You're trying to turn on either part, right? So for example, R and S are the two signal lines. So R in the beginning. So which one is R, which is S? So here's R, here's S, right? And don't forget that you have this. So if there's nothing to be connected to B, what's the voltage here? 0 volts. And why? Because there's no current. You don't have any circuit here, so there's no current flow through the resistor. 0 volts here, 0 volts here. No voltage drop across this resistor. So it's going to be 0 volts. So that's why, let's do it over here. R in the beginning will be 0. Okay? And S, what is S? Since 5 volts being connected to here, so here should be 5 volts. So what is happening is, at some time point, for example, this time point, A is being turned off, and somebody just changed the switch to the terminal B. And what's going to happen here is, when this switch leaves A, it won't be a solid off. It's going to vibrate for a few times, and until it's being totally turned off. Okay? And then there's need some time for this switch to fly. Okay? After this time point, right? You need the switch to fly, which is a juke. Switch cannot fly, right? It's really short time period, just show you that. And when it reaches B, so at this point, start leaving A, right? So at this time point, it's flying, and at this time point, it reaches B. So what's going to happen there? That won't be a solid on, right? So it's going to be turned off and on and off and on and off and on and off and on, right? Oh, no, not there, sorry. So that's 0 in the beginning, so it's going to be on the top. Turning on and off, turning on and off, turning on and off, and finally being turned on, right? That's what's going to happen for the mechanical vibration in detail, which you couldn't see by your naked eye, but it's going to happen. Okay. But however, if you have a debound circuit, you can protect your switch to make it solid on and off. So for example, you have a RS, right now the Q. So during this period, what is Q and what is Q bar? So it's being set, so Q is 1, Q bar is 0, right? And when you are trying to change S to 0, and you change this one to 1 before anything can be changed, it's just bouncing back to 0 and 1 and 0 to 1, which doesn't matter, won't affect the result. So during this process, you still get a solid Q to be 1 and Q bar to be 0. The reason is you have a 0, 0, 0, 0, which is a memory. Won't change won't toggle your result at all, right? So that's a memory. And after that, you have both of them to be zeros. That's a really solid memory process, right? Until here, you get a 1 here. So just one time, very short time period, vibrate to 1, and here's 0, and you are going to get a result of what? For this time period. You are resetting the circuit, so Q becomes 0 at this time point. Okay? And then next, it's going to be 0, 0, which will be the memory. It won't affect the result until it stabilizes itself. So nothing will be changed. Right? That's why it is important. Let's draw the entire circuit just in case somebody is getting confused here. Q bar, right? So that's why it's important to have a little buffering area between the power supply and, so here, for example, this is your electrical load. Here's the power supply. Okay, you need this kind of buffering area, buffering region, or switch to give you a pretty stable on and off, but not vibration instead. All right, so that's everything we need to know for SR latch and one of the important applications. So in the next lecture, in the next video, we are going to talk about flip-flops, which consists of SR latches. Thank you for watching. I'm going to see you in the next video.